the 10th day, and let's see, we did a test last time. You remember the time before that, we were talking about polynomial functions, and those were these functions that look like, I don't know, curvy roller coaster looking things. You remember that? Or has it been too long? Shall I remind you? You should have something in your notes about it. Yeah, we're still in the exam 2 packet. What do polynomials look like? They're smooth. What do the sketches look like? No? This thing, leading coefficient test, left, right-hand behavior, and we're trying to figure out, how to graph these. Is it a polynomial? Determine left and right-hand behavior. Find the x-intercepts. If the factor is raised to an odd power, it'll cross. If it's an even power, it'll bounce. And then plot everything. So we had just started that, and then I had given you an example, and we got stuck because we couldn't factor it. That's where we were. I know it was a week ago. Lots happened since then. So what I'd like to do is I'd like to, after I've looked at this a little bit, I'd like to kind of do it the way that the packet does it, because I think that will help you in your homework to be able to follow along with what they're asking. All right? And I think if we approach it this way, it'll kind of flow a little better, I hope. So look at this example. It's asking us to graph a function, capital F of x. I'm on page 51 of test packet 2. It's asking us to sketch or graph capital F of x equals 3 times x plus 5 times x plus 2, that quantity squared. So first, let's talk about the leading coefficient and the degree. Now, that was on your last test. So what is the leading coefficient? This is a little harder than what we've normally seen because it's already factored. Do you all see that you've already broken it down into multiple factors here? That means that to find the leading coefficient and degree, we would have to multiply it all out in order to figure out what the highest power is and what the number in front of that is. But there's a shortcut to it, all right? Here's a shortcut. Look at this x here. What's the power on it? Squared. So I'm just going to jot down here x squared. Times, now look at the other factor. We have x. What's the power on that factor, on that parentheses right there? It's the first power, right? Even though it's not written, there's a 1 there. So that factor really acts like an x to the first power, so I'm going to put that here. And then, what about a number? Do you have a number sitting out anywhere by itself? 3. Right? You see the 3? So that 3 acts like a 3. I'm just going to throw it in front of all this. So what's 3x squared times x? 3x to the third. So what is the leading coefficient then? 3. That's from this number right here. What is the degree? 3 also. Now, can you explain to me what the left and right-hand behavior would be, even though they're not asking for it here? What does the left side do? What does the right side do? Left side's down, right side's up. And that was going off of that table that I gave you. We have an odd degree and a positive leading coefficient. So you read off that table. Do I need to show that table, or are you okay with it? Y'all okay with it? Okay. So look back in your notes. All right, now we need to figure out what the zeros are. The zeros are the same as the x-intercepts. So what we do is we set the function equal to 0. All right, so for the zeros part of this, see, think about this packet. I don't have a lot of room to show things. I set it equal to 0. 3 times x plus 5 times x plus 2 squared equals 0. And what we need to do in order to solve that is factor it. But what? It's already factored, which is great, because I can set each of the factors equal to 0. How many factors are there here? Well, 3 is a factor, right? X plus 5 is a factor. X plus 2 is a factor, and it's actually squared. But in terms of an answer, we're only going to get one answer from this factor. So take each of these and set them equal to 0. And just the factor, you don't have to worry about the power. Not yet. We will, but not yet. Now, can 3 ever equal 0? No, so we ignore this one. What about here? X plus 5 equals 0? What's your solution here? X is negative 5. And then the last one here, X is negative 2. So how many zeros do I have? 2 of them, right? I list them out here, negative 5 and 2. I'm just going to stick them right here. Negative 2, sorry. And then they give you another place to write them, negative 5, negative 2. Everyone understand where these numbers come from? Yes? All right. The next thing is to find the number of factors. So we know that the negative 5, right, came from this factor, x plus 5. How many of these factors were there? 1. So I'm going to put 1. How many of the x plus 2 factors are there? 2 of them, right? That comes from this power, right? Because it's squared, that means there's 2 of those factors. So I'm going to put 2. Is this 1 even or odd? Odd. And 2 is even. When does it cross? When does it touch the x-axis? Do you remember? Odd. It crosses at odd, so we are going to cross here, and it will touch, or we said bounce, didn't we? We use bounce. We'll go with bounce. Everyone understand bounce is the same as touch, at least here, right? After we have all this information, we should be able to graph it. So here's where we start when we graph it. We start by putting the zeros, the x-intercepts. Where are they? Where are the zeros? Negative 5 and negative 2. So at negative 2, you put a dot. At negative 5, you put a dot. It's very important that you do this in the correct order. Put your x-intercepts or your zeros first. The next thing you do is you sketch the left and right behavior. So what should this function do on the left side? Go down, and on the right side, go up. So pick your point that's to the furthest to the left and draw a curve that comes down. Then pick your point that's furthest to the right and draw it going up. And then the rest of what we need to do is figure out what happens between these 2 dots. Right? Remember, that's the question mark that I was saying? What's that part in the middle? But we know that at negative 5, I must cross through the x-axis. So do you agree that when I draw this, I must come up and through like this? You'll see how I cross through? And then I have to come back and get to this 0 or this x-intercept, but when I get there, I'm supposed to bounce, right? So it's going to look like this. You want to see that? That's what we're looking for. Now, when you draw this on your page, it might look a little different for you. You might have done this where it came down a little sharper, and then you could have come way up with it, and then you could have come down like this and bounced, and you could have gone like that. That would also be a correct answer. We're going to have variations within our pictures, but they'll all have the same properties. They'll have the same x-intercepts. You'll have the same left and right behavior, and all of our pictures should be up on this side. None of our pictures should be below. Understand? If you want to know how high this went, if you actually want to know how high that function went, you do that in calculus, but you don't do it here. That make sense? Let's go through this next one. Start with the leading coefficient and degree. So tell me what this thing behaves like. And I think I'll start with the negative 4. Negative 4 behaves like negative 4, right? Okay, what does What does x minus 2 cubed act like? X to the third, just x cubed. So we ignore the number behind. And then what does x plus 4 to the fifth power really act like? X to the fifth. And what does x minus 5 squared act like? X squared. So the whole thing really acts like negative 4, x to what power? What is it? 5. Where are you getting 5 from? Nope. You're multiplying these together. So you're just going to add all the exponents up. See, because what happens here is this. If you were to actually take x minus 2 and multiply it times x minus 2 times x minus 2 3 times, the highest power of x that would come out would be x cubed. Then when you do this one, that would be a terrible multiplication. You wouldn't want to have to do that. But the highest power would be x to the fifth. And then this last one, the highest power would be x squared. So you would have an x cubed, an x to the fifth, and an x squared. The biggest power you're ever going to get from that is x to the 10th. So what is the leading coefficient here? Negative 4, and the degree, 10. What does this behave like, left and right-hand behavior? Down and down. Question mark, down. What are the zeros here? So you have to set each, because it's factored already, right? We're very lucky. This thing is already factored. So set it equal to 0. Plus 2, negative 4, positive 5. Anyone have a question on that? Y'all just need to let me know. Just setting each of these to 0. What about the negative 4? Is not here? Does that negative 4 come from this right here? No, negative 4 can never be 0, right? So you ignore that number. I just don't want you to accidentally grab this number down here because that's what students will do. If it's a number by itself can never be 0. But this whole thing right here could be if you let x be 2. This whole thing could be if x was negative 4. And this whole thing could be 0 if x was 5. That's where they come from. Understand? Okay, so list out our zeros. I don't know if they were trying to confuse you or they were out of room. But there should be 3 of them listed here, right? 2, negative 4, 5. Now the 2 came from this one, right? How many factors do we have there? 3? Is that even or odd? What happens if we have an odd? We cross. By the way, this number of factors and odd thing, this odd-even thing is called the multiplicity of the factor, which is why you'll see multiplicity up here. When we say, hey, you've got this polynomial and you've factored it, and they say, oh, you've got this one factor and it's, what's its multiplicity, even or odd? Because that's all you need to know in order to graph this, whether or not you touch or bounce or cross. How about negative 4? How many factors from here? 5? That's odd again. You'll cross. And then finally, the 5, number of factors. 2, even. That means you're going to bounce. Now, what's my next step? Plot your zeros. So 2. It doesn't matter because they're all going to wind up in the same place, right? No matter which way you put them, as long as you have all of them there. Doesn't matter which order. What comes after you plot the zeros? End behavior. Now, this can get kind of complicated, and your graph can really start to look crappy if you kind of jump the gun into your drawing. So what I like to do is just kind of remember this side's going to go down and this side's going to go down, right? I'm not drawing my graph yet. I'm just kind of getting an idea of what it's going to look like here. What am I supposed to do at this negative 4? Cross through. So I'm supposed to have a graph that goes down over here and crosses through, which means it's going to come up, right? Like this. So I'm actually going to, I think I'll do that part of it right now. And that's about it. Now, what happens at 2? Nope, careful. At 2, I'm going to bounce off of it, right? So when I draw this, I need to be sure that I come through here and give myself room to make a little turn there to bounce. Do y'all understand? So I'm going to come up here. I'm going to bounce off. That good enough for you? But wait, hold on. Where? 2 is 3 was odd. This is the -4. Where? Why does it bounce at 5? Hold on a second. Hold on. Look. This -4, right? This -4 is telling us where we actually have a 0, correct? This number is the power that came right there. That 5, that's odd. Odd tells us we crossed there. Understand? Okay, now the next one we're looking at was 2, yes? 2 comes from this factor. Yes? 2. Oh, I see what you're saying. Okay, 2 here. Because it's odd, we cross. That's what you were trying to tell me. Yes. Okay. So why did y'all agree when I first said balance? Hey. I'm not confused. The fact that I was confusing you should be a good thing, because that means you understand it correctly and I was just having a brain fart. All right, so we should cross here. And now at what? 5? 5 is where we bounce. So when I draw this, I want to give myself time to make the little bounce off, and then come back down. If you draw things correctly, all right, if you do, then your end behavior should all match up. Like you should never be drawing this and then say, oh, I'm going to bounce and come down, but your blue thing that I just put was up here. That would mean something's off. This make sense? See if I can confuse you again. Look, this one's different. They did not factor it for us, did they? All right, so let's see what we do. What's good is leading coefficient and degree are easy to get this way, aren't they? What's the leading coefficient? 1. That's the number in front of the x cubed, right? And then the degree? 3, so this should go down on the left and up on the right. But they do tell you something. They say rational just means fractions, okay? So these are numbers that are x-intercepts are -2, -1, and 3. They just saved us the trouble of actually trying to factor it, right? Because they told us where it's going to cross, or where it's going to hit the x-axis. So that means I can list these out, -2, -1, and 3. So no work was required. I'm sorry? But, okay. So how many of each of the factors did we have? So you tell me what you think. There's a way we can tell. Anyone have a guess? It is related to the end behavior, but let me highlight something and then you think about it. Okay, the degree is 3. That means the highest power of x that we could possibly have would be 3, right? Could this factor right here have 2 factors? Then it would be squared. It would look like something squared, wouldn't it? And then this factor, you have to have at least 1. Right? This would have 1 factor. That means you got an x squared and an x. And then you have another one, which means you would have an x squared, an x, and an x, which means you would have x to the what? 4th. And that's not, it's supposed to be x cubed. Let me try and show it a different way. They would have to each be 1. Look, this guaranteed is the way that this thing factors. That's what these pieces of information give us, don't they? Right? When I plug -2 in, I get a 0. So that's why it's the opposite of what I see. right? If I plug -2 in here, this thing becomes 0. If I plug -1 in here, it becomes 0. If I plug +3, it becomes 0. Do you all agree with this? The powers on these are the things I don't know, right? I don't know what the powers are. But the most it could be is 1, 1, 1, right? I could not have 2, 1, 1, because then I would have a 4th degree polynomial. I can't have 2, 0, 1, because if it was 0, then what? It wouldn't be there. So it has to be 1 for all of them. So it crosses at all of them. I'm just going to start putting O in E for even or odd. So, and then I'm going to put cross, cross, cross. Do you get it? So let me plot my x-intercepts, -1, -2. And that's not a whole lot of room. I think I'm going to change the scale on this. I'm going to count, this is -1, that's -2, and then to the right. Yeah, that's what I'm going to do. I'm going to say, this is 1, this is 2, this is 3, just to give myself a little more room. The end behavior, and I'm going to cross on all of them. So this should be fairly easy to draw. Cross through, cross through, cross through. Questions? There's no catch. Okay. You said it, not me. There's no catch. Now, if this were math 1414, you'd be bleeding out of your eyeballs right now and your ears. We push way further than we do here in a 1414 class. All right, so what else? Well, I mean, what do we do here? Start leading coefficient degree. It's already multiplied out, right? So all we have to do is identify leading coefficient. 2, degree. 3, down, up. Kind of getting used to that. How many zeros do we have here? They tell us, right? 3 of them. -3, -1/2, and 2. What about the number of factors? It's got to be 1, 1, 1 again because it's cubed. So the number of factors total, this right here has to add up to be whatever the degree is. What if this was 4th degree? Then we wouldn't know. One of these would be 2, wouldn't it? We wouldn't know, and we wouldn't have a way of knowing. Not easily. There's a way we could figure it out, but you won't have to worry about that. All right, even or odd? Odd on all 3. So cross, cross, cross. I think I'll change my scale again. I think I'll go out. Same thing? Okay, so -1, -2, -3. So there's an x-intercept. -1/2 would be here. And then 2 would be 1, 2, there. Down, up, and crossing through at each one. So again, I'm just exaggerating how high I went just to kind of remind you. You can go as high as you want, as long as you do cross through at each one and you make it nice. Remember, it's got to be curved. Polynomials are curved. You can't draw V's and, like zigzag. It's got to be nice and smooth. Number 5. Uh-oh. Degree and leading coefficient, we've got down, up. Boy, it's kind of getting boring. Down, up. Oh, we'll do 6. Looks pretty bad, doesn't it? All right, so this is the first problem where they have not given us it in factored form, but they also did not give us the zeros, did they? So our only option right now is to try and factor this ourselves. And I think I'll need a little bit of room for that, so I'm going to come over here and do it. I have to set the function equal to 0. Well, I don't see a GCF anywhere. I'm on number 5. But on number 6, you are correct. We will do a GCF. All right, so how do you factor something like that if it has 4 terms? Grouping, right? Grouping. But first thing would be GCF, which I don't have a greatest common factor. So I'm going to split this thing right down the middle, right after the second term. Looking at the first 2 terms, what can I pull out of both of those? X squared, what would be left? 3x plus 1. Now I need to get a 3x plus 1 in the other one when I factor something out. So what can I pull out of the other one? Negative 4. And you would be left with 3x plus 1. Very good for us. What does this turn into? X squared minus 4 and 3x plus 1. Yes, but look at that x squared minus 4. It's right. It's a difference of squares, and we need to recognize that, or else we're going to run into trouble. So I'm recognizing x squared minus 4 is a difference of squares. And now I set each of these factors equal to 0. Set that to 0, that to 0, that to 0. So we have x equals negative 2 from that one. We get x equals positive 2 from that one. We get x is negative 1/3 from the last one. So negative 2, positive 2, negative 1/3. Y'all see that? I'm going to go ahead and list those out in this little box here. Negative 2, positive 2, negative 1/3. How many factors of each do we have? It's 1 on all of them, right? Just come over here to the factored place. I'll just put the powers up here. 1, 1, 1. So 1 for each of these factors. They're all odd. We cross at all 3. Kind of getting bored crossing all the time. Maybe we'll bounce on the next one. This one, I'm gonna count out 4 spaces to be equal to 1. So 1, 2, 3, 4. That's 1, 2, and then the same thing the other way. If you want. Oh, you do it however you want. Yeah, I don't care. You know, I'm following these notes because, like I said, it'll be easier for you to do your homework if I'm doing what they're going to ask you to do. But in a normal class, what I just tell students to do is draw a number line, and then just plot the points like we have in this case, like negative 2. The next one would be negative 1/3. The next one would be like 2. And don't even worry about the spacing. Just get them in correct order from left to right, and then just show the graph. But because we're trying to fit it on a grid that's been supplied to us, we have to kind of mark things out correctly. All right. My x-intercepts are at negative 2, positive 2, and then negative 1/3, which is about right in here. It goes down then up, and it crosses through everything. Now, before we lose complete sight of everything and we just get into this very mechanical mode of like do the process without even knowing why we'd ever want to do this. Quick example, won't be tested on this. You can turn me off for a second if you'd like, or continue to keep me turned off. Let's say I own a company, I'm running a business, and I have to manufacture these boxes. I don't know, maybe I'm making, the first thing that came to my mind was I'm making like a server, you know, servers that you have in these big rooms, all these servers, and you have to make these like aluminum cases for these servers, and you put all the equipment inside. So I'm making these server cases, and I start with a sheet of aluminum or something that I buy from a company. They give me just a bunch of sheets of aluminum, and let's say that this is, I don't know, 14 inches wide by 20 inches tall. That's what I get from my supplier. And what I would like to do is I'd like to take this and I'd like to make the little case for it, right, out of this. I'd like to make a case out of this. Y'all okay? Yeah? Okay. So I'm going to come in with some machine and I'm going to cut the corners out, right? I'm going to cut these corners out. Oops. And after I cut those corners out, I'm going to fold the edges up. And then I'm going to weld everything together, all right? When I do that, when I fold it up, it's now going to look like this, isn't it? That's what it'll look like. Box I can put stuff in. Now this box has a bottom, has sides, doesn't have a top, right? What I'd like to know is how do I do this, cut this, so that I can get the most amount of stuff in that box. The most amount of stuff, right? Because I want to be able to put as much stuff in there as possible, right? So let me see if I can find a sacrificial piece of paper. This is a sacrificial piece of paper. So look, here's my aluminum, right? I'm going to cut the edges off. So I'm going to start my first example. I'm going to cut a very small edge out of this. What are you doing on your computer over there? What are you doing? Oh, okay. You're taking notes with your computer? Huh? Oh, really? You've always done that? Oh, okay. All right. Sorry, it's taking so long. There's my container, right? And imagine if it were welded on the sides, I could fill it with, you know, water, and it would hold a certain amount, right? That's what we call the volume of this. Now, that's one design. I could also do this design. These are supposed to be squares. Like, they're all supposed to be the same, okay? Fold these up. Here's another version of the container, right? Yes? Which one holds more? Or do they hold the same? Does it matter where I cut? You understand the question? Does it matter? What do you think? Do you think these hold the same amount? How many of you think? The what? Okay. Sure. Okay. Well, let's just say volume. Let's just say liquid, okay? I mean, which of those would hold more water if I could pour water into those? Or would it be the same? Or are they different? What do you think? So let's just take a quick vote. How many of you think that that will be different? Different volumes. They will hold different amount. How many of you think that they will be the same no matter what, no matter how I cut it? Okay? Well, we could argue about it. We could sit here and have a nice discussion over cold beverages about what we think might be true, but it's very simple to figure out what's happening here. And Let me show you how. I'm going to come in here and I'm going to say this part that I'm going to cut out, I don't know what it is, but I'm going to call it X. So that means that this is X, and 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 this is X, right? So I'm cutting out a little square, X by X. I don't know what it is, but that's what I'm going to cut out, right? So when I fold up that first edge, after I cut out, right, here's my picture over here. How long is this? How long is this side? Look at where it came from. It was 14, and I took away how much from each side? X and X, so take away 2X. So do you agree that this side on the front is 14, take away 2X? Yes? How long is this? 20 minus 2X. And then how tall is it? X, right? Because that's the part you fold up. You all understand that? This is X. What is the volume of a box? Length times width times height, isn't it? Length times width times height. Yes? That is a polynomial function, isn't it? That's a polynomial function. And so could you graph this? Absolutely. What's that? Because, okay, no, and I'm only posing this to you because this is a real-world application, all right? This is a polynomial function. So since it's a polynomial function, I can tell you right now, if I went through all the work, it's going to have 3x intercepts. Let's see, there's one at, what do we have here? 7, at 10, and at 0. I know because of degree and leading coefficient, I know that the end behavior is, let me label these, 5 and 10. Right, so I know it goes down, up, down, crosses through at all 3, right? And what I want to know is when this is the highest it can ever be, right? Yes? Because I want to get the most volume out of this that I possibly can. That highest point is here, which I said you have to take calculus to be able to find that, don't you? But what I can tell you right now is just from the picture that it does matter. It does matter where you cut it, because it appears that when you get close to 0, the volume's not that big, right? It goes up, but then it comes back down. So as you get closer to 7, it starts to decrease also. Somewhere between 0 and 7. So somewhere between, remember, 7 would be halfway across, wouldn't it? Somewhere between not cutting anything or cutting all the way halfway across. Somewhere between there, you have the most volume you could possibly get. Do you see that? Now, you have to be able to go and find that point in calculus. But to investigate functions, to take a real-world situation and then connect it to a function means that you have to know how these behave. Like I have to be able to look at that and know it's a polynomial that's smooth and curved, x-intercepts, at left and right behavior, bounce, touch. That tells me a lot right now, right? Just by looking at this. Look at between 7 and 10. What's the volume? It's negative. So it doesn't make any sense. Why? What x was how much I cut, right? If I cut the corner out of here, if I go past 7, aren't I going past halfway? And then when you try and cut from the other end, there's nothing to cut. So like 0 to 7 is the most you can ever cut. That makes sense, right? So anyways, everything we try and do in the real world with mathematics is we take a situation and we try and relate it to something mathematical, and then we study that mathematically. Do you want to know what it would be? Do you care? Nah. Oh, I guarantee you that all those companies do, these are called optimization problems. They all do optimization because you don't want to be wasting material, right? I mean, there's a way I can make a box that could hold a certain amount, but when I cut this out, right, when I cut this stuff out, that's waste, isn't it? That's waste. And I could say, then just cut a little bit out. But we know by cutting a little bit out, I'm not going to get much volume. So I want to know, how much do I cut out to get the most volume? And then I'm getting the most bang for my buck. You know what I'm saying? It turns out that soda cans are designed in a similar principle. They all you want to hold 12 ounces in an aluminum can. The dimensions of that can are solely based upon finding that optimum point. So, I mean, think about not a plastic bottle, but like aluminum cans. You could have a 12-ounce can, right? That could be 6 feet tall and like, you know, like a pencil almost, right? That would hold 12 ounces. You'd be like, you know, that's a lot of aluminum though. Or you could have something that's like a big wafer that's only like this tall and you have to hold like that. You're like, you know, but that would be a lot of aluminum too. Somewhere in between a tall, very, very skinny can and a very, very wide, short can, there's an optimal way to make a 12-ounce can to use the least amount of aluminum. And that is where the dimensions of a can come from. It's not because it fits into your hand nicely, or it's because they use the least amount of material that way. But they don't do it just by just going, bad bitch, me, who cares? You know, you're making millions of cans, and they're each costing you, you know, money. You don't want to. Your business won't survive if you just throw money away, right? I think the koozie came after the can. Oh, I didn't tell you all this story. I'll tell you, speaking of koozies. So my daughter's going into first grade, right? She's kinder, now she's going to first grade, and she's really learned how to read. Like, she's really impressed me. And so we're at the river before the semester started with my in-laws, and we're like, I'm sitting there bragging about her, and we're sitting there, you know, drinking beer under the little canopy out on the river, and yeah, you know, Maddie, she's reading and everything, and la la, and I'm all showing off, you know, talking about her. And then lo and behold, this little koozie comes floating down the river, right? And she grabs it, she's like, Daddy, you know, look, koozie, and it had something written on it. I'm like, hey, read that to your uncle, you know, read what's on there. It says Frio River Whores on it. And she's like trying to read it, and she's like, Frio, she knew Frio, she's like river, and then, ooh, and you know, I was like, come on, you can do it. So, I didn't know what it said, you know, and I mean, I'm not thinking that's what's going to be floating down the river, you know, and then I grab, I'm like, oh my God, forget it. Just need to lock her in a cage so she's not exposed to stuff, you know. No, we just kind of like, you know, hey, look, it looks like, I think I saw a minnow, you know, and just kind of got our mind off of it. But it was funny. Yeah. So I kept the koozie, you know, memories. All right. I hope that maybe by that little box example, you kind of see that we don't really just do this just because we enjoy this. I mean, there's always something in the real world that motivates the math. That's usually the way it works. All right, next one. What's the degree? I can't believe I told you the Frio River horror story. Leading coefficient is 4 on video or recording. I think it's a group, like a club or something. And then, you know what's funny is right after that, another koozie came floating down, and it was for a rehab clinic. It was like API rehab something or another. And I'm like, probably, I don't know. It's like that whole group got flipped over way back there, and you know, all their. All right, so the degree is 5, leading coefficient is 4, which means again down up. It's kind of getting tired of this. And you need to be able to now try and find the x-intercepts, which means you have to set that equal to 0. And it looks pretty ugly, doesn't it? Always pulling out GCF first. Just makes life a lot easier. Okay. So does everyone see that? Common factor for all these, 2x squared. So I pull 2x squared out. What would I be left with? 2x to the third plus 5x squared minus, careful, 2x minus 5, close your parentheses, equals 0. Yes? Now, the part that's in the parentheses has how many terms? 4. So, group it and hope for the best, right? So this is equal to 2x squared, parentheses. What can I pull out of the first set of parentheses there? X squared. What's left? 2x plus 5. Then the other set of parentheses right here, or the other two, I need to pull something out and be left with 2x plus 5, negative 1. Close off my parentheses twice, right? Because remember, this 2x squared was out here in front of everything. What does all of this right here turn into? X squared minus 1, 2x plus 5. What was out in front of all of that? 2x squared. Good. And the the x squared minus 1 was a difference of squares. No, because in grouping, the whole idea with grouping is that this factor will come out of both, but it only is represented by one factor. All right, I need to set this equal to 0, right? Well, you have to set every factor equal to 0. Set 2 equal to 0, x squared equal to 0, x plus 1, all of these, right? Can 2 ever be 0? Nope, so you're going to ignore that one. How about x squared? I want you to look at that this way. Do you agree x squared is really x minus 0 squared? It might help you see that that is a factor, right? That is a factor, and it's actually squared, which is going to tell us about bouncing or crossing, isn't it? And the 0 is actually just 0 itself, right? That's what makes this 0. What about from this factor here? This one, x plus 1. Negative 1. The next one. The next one equals negative 5 halves, or negative 2.5. Understand? Solve that, set that equal to 0. You should get this. Let me put these on my list over here. 0, negative 1, 1, and negative 5 halves. Yeah, 2.5 if you want. All right, how about the number of factors? For the 0, how many factors? Where does the 0 come from? It comes from this one, which was squared, right? So 2 factors there, which means that it's even, which means we will bounce, right? Is that okay? How about the negative 1? 1, which means it's odd, which means we'll cross. 1, there's only one factor, odd, we'll cross. And then finally, the negative 2.5 or negative 5 halves, one factor, odd, will cross. I'm using B instead of touch, right? T? All right, B for bounce. Plot your x-intercepts. 0. I'm going to go 2 tick marks will be equal to 1. Okay, so there's 1. And then here's negative 1. And negative 2.5 would be there. Is that all right? This is like 1, -1. This is 0, -2.5. Now I'm supposed to go down and up on the ends, right? And cross through everywhere except where? At 0, I'm supposed to bounce. So watch, check me out here. I'm going to start down here, go up, cross through, bounce, cross. Something like that. Be very careful when you're doing this that you are drawing a function. Remember, all functions must pass the vertical line test. So your final product should pass the vertical line test. What do y'all think? Oh, that's it, huh? Homework. This is kind of fun. No, I don't know about fun. For each of the following, use end behavior and x-intercepts to match it to its graph. So like you would have to basically go through the whole process that we just did and match it. Let's take a break. I know it's a little early for a break, but we're about to start a new topic, so we'll come in and start from scratch. Everybody ready? Let's get this over with. Okay, so as a quick review, what we can graph, right? What we can graph up to this point: lines, quadratics, polynomials. In fact, we even said that a quadratic is a polynomial, and a line is a polynomial, but polynomial is a more broad classification of functions. And so when it comes to a line, it was relatively simple. Y-intercept, slope, draw a line. Quadratic, well, that's where we figured if it opened up or down, then we did vertex, and then we did a quick sketch, and we went through a 7-step process, which was on your test. And then polynomials is what we just finished doing, right? Now we have a new classification of functions, 57, which are called rational functions. And what we're going to see with these rational functions is that they have a lot of characteristics that are not present in these, all right? So they look a lot different than this group of functions. We're going to have to be looking at domains a little bit more. We're going to have these things called vertical asymptotes, and we'll talk about what they are. But let's get to the definition. A function of the form p of x divided by q of x, where p of x and q of x are polynomials and q of x is not 0, is a rational function. I know that looks all weird, okay? But let me just give you an example next to this, what I'm talking about. This right here would be a rational function. That's an example of a rational function. What makes it rational is the fact that you have a polynomial on top, right? X squared plus x minus 2 is a polynomial. I mean, it's quadratic, but we said all quadratics are polynomials. And you're dividing it by another polynomial, right? P of x is the top polynomial, Q of x is the bottom polynomial. As long as this is defined, then it's a rational function. So we want to make sure that the Q of x, this bottom one, is never 0. If it's 0, we have division by 0. You're not allowed to have that. And this group of functions is the hardest, by far the hardest to graph, because there's a lot going on here. So when is the rational function undefined? When would we not be able to define this function? Well, that would be anywhere that the denominator is 0. Good. So you act like you don't like this. Okay, good. The places that we would have division by 0, all right, anytime we have undefined values, all right, are referred to as the vertical asymptotes. Or they could also be a place where we have a hole. We could have a hole in the graph, or we could have a vertical asymptote. I'll describe what these are, but they're two different things. I'm not quite sure what D is saying. Basically, I believe it's saying that these piece of information will help us determine the graph of the rational function, right? What it looks like will be dictated a lot by what, what's going on here where it's undefined. Okay, so let's look at this one. Determine the restrictions of the domain of f of x equals 3x over 5x plus 20. So what is it that's going to cause a problem is what they're asking here. What's the domain restriction? So we know that we can never have division by 0, right? So we look at the denominator and we set it equal to 0. When we set that equal to 0, we get what? Negative 4. The restriction, a problem, okay? So the restriction is that x cannot be negative 4, right? So to figure out where it's undefined, we set the bottom equal to 0, and then whatever we get as that solution, we don't want that as part of our domain. So the domain is all the real numbers except negative 4, which can be written this way. Negative infinity to negative 4 union negative 4 to infinity. Now let's see if we understand what that means. This is interval notation. Doesn't negative infinity to negative 4 with the parenthesis on the negative 4 mean everything to the left of negative 4? And then this one right here means negative 4 to the right forever. And because there's a parentheses, we don't include negative 4. So that's basically the entire number line taking that one number out, right? Negative 4. So that's our domain. So when we draw this picture, when we draw this graph, at negative 4, our graph should not be defined. Now, when we were doing polynomials, I had shown you some pictures, right, of polynomials. I'd like to show you the picture of this polynomial, all right? I mean, this rational function. Let me open it up here. I should have something I've done with this before. Here we go. Rational functions, new. Oh, good. I get to I wrote this one up where I just put in the top. The top was 3x, right? The bottom was 5x plus 20. Oh. It didn't like that. Here's the graph. What's in blue is the graph. All right? This dotted line that goes across, we will talk about that in a little while. That's called the horizontal asymptote. But look at what's happening at -4. 1, 2, 3, 4. If we go straight up, our graph does not actually ever get to that point. Our graph to the left goes up and up and up and up forever, but there's this like imaginary vertical line that we never get to. All right? And then the same thing happens as we come in to -4 this direction, it dives down. But if we were to actually go to -4 and look straight up and look straight down, we would never have graph. All right? That's what's referred to as a vertical asymptote. A vertical asymptote, think of it as like a barrier, this imaginary barrier that when your graph gets close to it, it either goes up or it goes down. All right? So let's look at the restrictions on these. Let's do 2. What we know here is that x squared minus 20 minus 25, right? We want to know when that's 0. And we're going to throw those answers out. So you have 2 choices here. You can move 25 to the other side and take the square root, or you can look at x squared minus 25 as a difference of squares, right? So move it to the other side. You want to do that? And then you take the square root on both sides, and whenever you take the square root, you always have to do plus or minus. Remember that, right? Plus or minus the square root of 25. What's the square root of 25? 5. -5 squared would be 25. So we actually have 2 places where we do not want our function to be defined, right? So our domain is going to be everything except -5 and everything except +5. So let me try and do that with the interval. I start out at -infinity all the way till I get to where? -5, don't want to include it. Then I want to go from -5 on the other side to where? To 5, and then stop, and then jump over 5 and go from 5 on forever the rest of the way. You see that? Writing it this way removes -5 and removes 5. How about 3? Yes. Yes? -5 to 4, -5 to 5 means on a number line. Here's -5. Here's 5. It means all the stuff in between. Yeah, we don't want to look at it as like a point, an ordered pair. Yeah. I know that's one thing. The notation in math, there's no real distinction between a point and an ordered pair, so it can be confusing. Oh, like in inequality. This one little piece would be that x is between -5 and 5. But that's a different notation. No, we want to do interval notation. I mean, that wouldn't be wrong. It's just not the notation that we're using. How about the next one? You just don't want the denominator to be 0, right? Can 15 ever be 0? No. So there's no restrictions. Because 15 cannot be 0, right, ever. And so the domain is everything. Yep. So everything, when we draw that function, it should exist everywhere. In fact, it's a line. I don't know if you can tell that, but that's just a line. You get the idea? On the next one, I won't do it, but you would set this denominator equal to 0. It's a quadratic equal to 0. You'd have to factor it, set the two factors equal to 0, and remove those from your number line. All right, y equals 1 over x. So this is a classic example that's given to help us see how this rational function behaves. Y equals 1 over x. So I'm going to do this here. Y equals 1 over x. Or if you want, you could say f of x is 1 over x. Either way. Is that a rational function? Yes. It's a polynomial divided by a polynomial. What's the domain of this? What can you not have happen? X cannot be equal to 0. Right? Which means negative infinity to 0, union 0 to infinity. Everything except 0, right? So when I draw this and I go to 0 and look up and down, I shouldn't have anything, right? So let me try and start getting a graph together here. And I'm going to use a t-table to get some points to try and see what this how it behaves. This is not the way we graph rational functions, but this is a good example to show you how these things behave. So let's first plug in 1. What happens when you plug 1 into this function? 1 over 1 is 1. So if I go out 1 unit to the right and go up 1 unit and I put a dot, that point lives on my graph, right? Let's try 2. Plug in 2, what do we have? 1 over 2? 1/2? 0.5? Yes? So we go to the right 2 and go up 1/2, which will put us about there. Understand? We plug in 3, we'd be where? 1/3, right? Plug in 4, we'd be at 1/4. Plug in 5, we'd be at 1/5. Plug in 10, we'd be at 1/10. What are those doing? As we go out to the right, the graph is getting smaller and smaller, right? Now, does it ever reach 0, though? No. I can go out to 1,000,000. 1 divided by 1,000,000 is a very, very small number, isn't it? But it's not 0. So what my graph is doing here is it's going down. And how do I tell you that it's going close to 0 without getting there? What I do is I draw a dotted line, right, like this. And so my picture, shouldn't have put my arrow there, but you can kind of see it goes and gets closer, kind of like gravitates towards that dotted line, right? It's almost as if the dotted line is pulling our function towards it without ever actually getting there. Understand? That dotted line is called the horizontal asymptote. Asymptote is one of those words that's spelled weird. It's there's an M in there and a P that you don't really say. Asymptote. Asymptote. So it's a horizontal line, right? That acts like a magnet and kind of pulls your graph towards it. All right, let's try some other numbers. How about something closer to 0? Like, we know we can't plug 0 in, right? We already said that. Let's try 1/2. Let's move to 1/2 right here. If I plug 1/2 in here, what's 1 divided by 1/2? Do you remember how we do division? We flip, multiply by the reciprocal, we get 2. That'll be 2. So I go to 1/2 and I go up 2. I'll be up here. What happens if I go to 1/3 instead of 1/2? If I plug in 1/3, it's going to be 3, which is going to be even higher, right? What if I do 1/4? 4, 1/10, 10, 1/100th, 100, 1/1000th, 1,000, right? The closer I get to 0, the higher up I am. And so what we're getting is our graph turns up here. But we already said that at 0 it's undefined, so there's this dotted line that goes vertically that I'm not allowed to cross over. And that's called our vertical asymptote. I'll refer to these as we move on as VA and HA. Vertical asymptote, horizontal asymptote. All right, that's what's happening over there. Now let's look at the other side. What if I were to have plugged in -1? What would I have gotten? Plug -1 in here. 1 over -1? -1. So I would have been down 1. What happens if I would have plugged in -2? You get -1/2. So -2, I'd be about right there. What about -1/3? I mean, sorry, -3 would give you -1/3. -10 would give you -1/10. And so what's happening is the same thing that happened on the right side is happening on the left, but we're coming up from the bottom, right? So it's looking like this. And we have our horizontal asymptote, which is the same line as the one out here, right? Just if you were to extend that all the way across, right? It's over here like this. How about if I try and plug in something like -1/2? That's going to be -2. So that's going to give you -2, you'll be right here. Then if I plug in -1/10, it'll be -10, way down here. And so on and so forth. So what you're getting here is it's diving down like this again, and there's your vertical asymptote, which is just an extension of this line straight down, and you get that. And this is a classic rational function that we use to demonstrate behaviors of these things. Not all of them look like this, but it gives us a sense of what a vertical asymptote looks like. It gives us a sense of what a horizontal asymptote looks like. What this one doesn't have is an x-intercept. And if we look back at this one, do you see now with this picture, that was the one from the very beginning, we have a vertical asymptote happening at 4, right, -4. We look like we have a horizontal asymptote. Can't really tell how high that is off the ground. Doesn't quite look like 1. But I also have an x-intercept here, don't I? A place where the graph crosses the x-axis. The one I just did by hand did not have a place where it crossed the x-axis, right? This graph never touched the x-axis. It can, it just, this one doesn't. This particular example doesn't, right? This example, look, it actually touched the x and y axis. But it was a different rational function. This was 3x over 5x plus 20. Okay, with all that in mind, let's continue. Asymptote. I'm not sure I'm going to like all this. A vertical asymptote is, let's do that part. A vertical dotted line which acts as a barrier and forces function what? What does it force the function to do? You have this barrier and you get to it and the function goes, and does what? Up or down, depending, right? It's going to force and forces function up or down. Now, which way it goes is going to be left to us to determine. We're actually going to have to investigate that a little further. But what we do know is it's going to go up or down and never cross. To find a vertical asymptote, the function must be in proper form. In other words, factored form, sorry. Factored form. So we want to factor it out. And then we want to set what to 0? Which part? The top or the bottom? Denominator. Which is called the denominator. Denominator is the bottom. Wherever the denominator is 0 is where it's undefined. Where it's undefined is where you have vertical asymptotes. You can have more than one, right? You can have more than one. How many vertical asymptotes are possible? More than one. As well, anywhere from none to whatever, really. Well, I shouldn't say whatever. I should say highest power of the denominator. Right? If your denominator is a quadratic, the most you could possibly have would be 2 vertical asymptotes. If your denominator is a cubic, third-degree polynomial, then the most you could have would be 3. And so you'll always be able to know the most you can have. So what are the vertical asymptotes of these rational functions? So what's the vertical asymptote of this first one? X equals 6. You get that by just setting the denominator equal to 0, right? How about this next one? Set the denominator equal to 0 and factor if possible. And this one it does factor. Yep. -8, positive 2. And then solve those and you get +8 and -2. Just be careful there because remember, when you factor it, you then have to set the factors equal to 0. So it's your solution to the equations is your vertical asymptote, not the factors. So the vertical asymptote would not be -8, it's actually +8. How about this one? Set that to 0. 3 and -3. 3 and -3. Those are the vertical asymptotes, aren't they? These are your VAs. Whoa. This is your VA. These are your VAs. These are your VAs. Now, it also is asking us to find the y-intercepts. How do you find the y-intercept of a function? Remember where it hits the y-axis? What can you tell me about any function where it hits the y-axis? No. You set the x to 0, right? You set the x to 0. To find the y-intercept, you set x to 0. So that means you plug 0 into the function, don't you? So look at this one right here, the number 1. Let's find the y-intercept of this one. So f of 0, this will be my y-intercept. And that's, what, 7 over -6? Yes? Yeah, you have to plug 0 into this whole thing. -7/6. No, y-intercepts. We've stepped away from the asymptote for a minute. How do you find the x-intercepts of a function? You set the function equal to 0, right? The whole thing to 0. But let me give you a shortcut, all right? For rational functions, if you set a rational function equal to 0, all you have to look at is the numerator equal to 0. That's all you have to look at. So here's why. If I tell you that a fraction is equal to 0, right? I set a fraction equals 0. A over b equals 0. Couldn't I always multiply both sides by b? And wouldn't the b's cancel here? I'd be left with a, and then what's 0 times b? Still 0? So setting a fraction equal to 0, the only thing we really have to do is set the a equal to 0, set the top to 0 to find the x-intercepts. All right, so look, for this first one, the x-intercept, what I do is set the top equal to 0. That's all I have to worry about. I move 7 over and I divide by 2. So move 7 over, becomes -7, divide by 2. And then I take square root. What's going to happen? Square root of a negative number is imaginary, which means we will have no x-intercepts. So for this function, the vertical asymptote happens at 6. It has a y-intercept here, and it does not have any x-intercepts. That's what I know so far. Remember, the goal is going to be to sketch these, to graph them. What about this one? The vertical asymptote, 2 of them, 8 and -2. How about the y-intercept on this one? So y-intercept, you plugged 0 in, right? And you got 5 over -16. Yep. That goes to 0, that goes to 0, that goes to 0. So all you have is the 5 over -16. What about the x-intercept on that one, though? Set the top to 0. -2.5. So this one had 2 vertical asymptotes. It had a y-intercept and it had an x-intercept, didn't it? Last one. What is the y-intercept of this? -1. How about the x-intercept? Set the top equal to 0. And it's a quadratic, isn't it? You have to factor it. I believe -3, -3. So you only have one answer, 3. So I hope what you're kind of getting to see here is that we can determine a lot of what the pictures of these look like by just looking at the function itself. We can figure out where the vertical asymptotes are, the y-intercepts and the x-intercepts, just by doing some algebra, some analysis of the function itself. How much further are we going with this? Hold on. Well, you're kind of very lucky. You don't have to. We're not going to graph these. Is that okay with you? All right, good. All you're ever going to have to do then, it appears, is find the domain, vertical asymptotes, and the intercepts. That's kind of lame. We don't graph them. It's great. That's our theme. All right. Try these first 2 on your own. See if you can find the domain, the vertical asymptote, or totes if there's more than one, and your x and y intercepts. Y'all seen Dazed and Confused? It's an old school movie, I guess. I can say that. You know, it's the last day of school. They all get out and start running around crazy and throwing toilet paper out the windows. And so that I want to see that after the final. This is the last math class. I want to see some celebration. No paddle? No? No hazing? Okay. If you have a question, raise your hand. I'm happy to come by and help. You know, making progress? Some of you all look dazed and confused. No? That's why we take notes, so we have something to refer to. I have yet to meet any student who can listen to me for 3.5 hours and recall it all verbatim. If you don't take notes and follow along, then you have nothing to refer to later and you're hung out on a limb. That's part of being a good student, is understanding how to do that properly. Yep. X equals the number. Yep. No, because it's a vertical line, and we define vertical lines, X equals a number. That's where your graph will never touch, yes. I'm going to start filling in some of this and see if you're getting this or not. Anybody want to tell me what the first one is? 6 here? Good, that's correct. What's the VA here? It's still 6. You set the bottom equal to 0. One, 6. X. Negative. Yeah, I put them up there. Just 1 and 2. It's good. What do you think? -1 and then -1, 2, and then 2? We'll see. We'll take a vote and see if people agree with that or not. Yeah, you want to put them in order like you'd read a book from left to right. You have -2? Okay, so let me see. Hold on then. You set the denominator equal to 0, right? And you factor it. I'm out of room. X minus 2, X plus 1. Then you set the factors equal to 0. And that gives you +2 and -1. Yep. That's what I was saying earlier. Be very careful because a lot of people will get to the point where they factored it and then they use that number inside as the number to throw out, but it's actually the opposite of what's there. Oh, you did the other way. Okay. Except that it's -1, not +1. Yeah. Okay. How about the vertical? We have 2 of them, right? At -1 and 2. So, yeah, so that would have messed both of those up. And then how do you find the y-intercept? For y-intercept, you plug 0 in for x. So all you're left with is the 3 over -2. To find the x-intercept, that's where you set just the top to 0. Is that okay? Understand? I'll leave it there. Yeah, the graphing, I'm happy for you. It's a lot less stress to not have to graph it because there's a lot more involved in graphing this by hand. I don't know if it's in test packet 3. We'll see. I don't even know how far we're going to get into that packet, to tell you the truth, right? We only have one more class after this, and then a final. Yeah, next Thursday is our final. So after today, we'll have one more class, and then we have our final, and then we're done. I hope not. I've got plans. I think July 30 is end of term. And then if you're taking classes in the fall, I think we come back on 20th. I think we got almost, I know I've got 2 weeks off after 3 weeks for students. 24, oh, maybe I get more than 2. I don't know. I think, don't we come back on a Tuesday? It's a Monday? 24th. Okay, yeah, I come back on the 17th. Well, we come back as faculty on the 17th. So I'll get, yep. One more. We're definitely not going to rush through it. All right. That's it for this. I think that should be enough as far as those. Now, here's an application. And really, I just want to show you this because it's where these functions are used. It's used a lot to model things like this. Heavy metal contaminants in a cement quarry may be removed from the soil by planting sunflowers. Well, I didn't know that. If S is the number of sunflowers in thousands and P is the percent removed, then use the following model to estimate the number of sunflowers needed to remove P% from the contamination. All right. So it says, remember, P is the percent in whole numbers, and S represents the number of sunflowers required in thousands. Let's look at this. This is a rational function. This model was created for this sort of situation. How many thousands of sunflowers would it take to remove 50% of the contamination? So what do I need to do here? Set P to 50. In other words, I need to find S of 50, which means 90 over 100 minus 50, which is 90 over 50, right? Which is 9/5, which is what? 1.8. So 1.8 thousand, which is what? 1,000 would be 1,000. 1,800? 1,800 sunflowers. I don't really. Really? Really? I've never noticed. And then they sell the sunflower to kids, and then the kids die a month later, and they're like, what the hell happened? I'm just saying, like, they get all these contaminated sunflowers, and they're, giving them away. I guess the sunflower gets rid of it somehow, huh? Absorbs it and gets rid of it. That's why they're always giving away sunflowers, huh? Here, take them. How many thousands of sunflowers would it take to remove 99% of the contamination? 99, right? You're just plugging in 99? So, yeah, 90 over 1, which is 90,000, which is 90 sunflowers. What this example is trying to get you to see is that you can't remove 100% because Yeah, the only way to get 100% is to try and plug 100 into the function, and then what happens is you get 0 on the bottom, right? Now, what I'm going to do, so what percent removal cannot be achieved? 100%, right? That cannot be removed because you'll have division by 0. So what I'm going to do is I'm going to graph this. It was 90 over 100 minus p. So 90 on top, 100 minus x, I have to use x. And then I'm going to zoom out. I can't change my x coordinate. Just adjust something here in my code real quick. Where is it? What's going on here? There we go. Ah, why didn't it? Hold on. Trying to figure out where my range, there it is. Okay, that's better. So here's the model for this function. And notice that as we go out, this doesn't look right either. Oh, they changed it. Okay, thank you. 90, 100 minus x. Thank you. There we go. So look at this function. Do you see it's a rational function? We have this thing going up, and on the other side it's coming down, right? That's the function. But in terms of p, we can have 0 sunflowers, or we can have the most is 100. And what happens is you get closer to 100, then the number of sunflowers becomes infinite, and so there's no way, you just can't get all of the contamination out. It's a model, okay? This is a model. What we're saying is that you need a model that somehow doesn't allow you to remove 100%, because it would be impossible to put that many flowers into the ground, right? Because think about it, if a sunflower is only good at removing contaminants in this area, then how could you get every piece of everything covered? So we want a model that does something really bad at 100%, and this function will do that for us. What would happen in the real world is that you would make a model, you would work backwards like this in the real world. You would do an experiment. Here's P, and you would say, okay, we removed 10% of the we removed 10%, and we had to plant 90. We had to plant 1,000 sunflowers for that to happen. Okay, so you actually go out there, you plant 1,000, you realize you've removed 10%, and then you go and you say, you know what? Let's put in 1,000 more, and you realize that you removed a different percentage, whatever it is. Okay, and then you say, okay, let's do 1,000 more. Maybe you did 1,000 more the next year, and you realize that you had more. Then you realize that we can fit a model to this, right? We can actually find a function that's behaving that way, and that's called regression analysis, where you take data points and you find a function to fit it, and it's called a best fit function. Have any of you ever used Microsoft Excel? Anyone ever use Excel? Have you ever used their fit regression model? Okay. Hey, I'm keeping us out of test package 3. The longer I have this. Okay, so look, let's just make up some stuff. Let's say you have a day. Oh, I can bring up something that might actually be relevant. Hold on. find it. I'm afraid to open this. No, that's not it. Yeah, it's the pictures from the Three Rivers Horrors. No. It might be on my desktop. There we go. There we are. So last semester, I had this goal of losing some weight because I was kind of, getting married. You get married and you kind of lose sight of things sometimes. So I had this goal last semester, at the beginning of the semester. I weighed 198 pounds, and my goal was to get to 174 pounds by the end of the semester, which I reached my goal. I stopped keeping track of it, and then I've been having fun, so it's gone back up. But what I did is every day I took I weighed myself in the morning, every morning. And I was working out, and I was keeping track of, oh my God, I was keeping track of so much stuff. I was keeping track of my calorie intake and my, what I was eating and what I was burning and exercise and everything else. And so I know it's kind of disgusting, isn't it? No, just every day I just put in my numbers. I was using an app called MyFitnessPal, and I would exercise, and I put in my heart rate monitor, would keep track of my calories, and I just put in how much I burned, and I kept track of what I was eating. Anyways, so look, this line right here, okay, what happens, this line, let me see if I can right-click it. Format trend line. So you put in all your data, and then the Excel spits out this what's called a scatter plot, which is all the different days and the weight. So I would fluctuate up and down, right? And I asked the computer to please give me a line, a linear model, a linear regression that would represent the best fit line to this data. Do you see that? And so what I could do with that line is I could predict when I was going to reach my goal. See, this is the days down here. So I say, look, if I continue on this trend line, I can predict that right there. The equation of that line is negative 0.3978x plus 16,922. That's a line, isn't it? Yes? The computer has supplied me with the function. That's the way the real world works. You have this data, you fit a model to it. Once you have that model, then you can do whatever you want. Now, if I wanted to do something other than a line, I could try a quadratic, which would be a polynomial of degree 2, right? A quadratic. And now what it's going to do is it's going to try and fit a quadratic. So you see that there's a curve to that line now? Can you kind of, not line, do you see that that's curved? That's a parabola. And then the equation of it is up here. 0.0018x squared minus, so now it's come up with that function for me. So what we do in this class is we often give you the function and say, okay, let's do this and this and this and this and this. Real world, data, from data to function, and then you do the analysis. And I could fit all sorts of things to this. Let's see, we haven't done exponential, but that would be the next thing on our list in packet 3, exponential functions. So here's the exponential function that it fit to this. Now, what makes more sense, though, is not a line, though. Do you agree? I mean, the real world. If I continue working out, right, forever and ever, am I going to follow that line? No, because eventually I get down to like bone, right? And at that point, I can't lose. You know what I'm saying? Like, if I continue on a line, eventually I'll go to weight 0. And that we just know that that's not what's going to happen. Just like the sunflowers, we know that there's no way we can remove everything. So a line is not a good fit. Something like a logarithmic function probably would have been better. And then I can mess with it. Because, see, logarithmic functions have asymptotes this way. And so I could say, look, I know that the minimum weight I'll ever hit is like 150 or something like that. And then it would be a good model. Yeah. I used to do triathlons a long time ago. And I know how to drop weight fast if I have to. And so, like, look at this number right here. This is a line, right? This line model. What does the number in front of X represent? Yeah, it's your slope, right? But in this model, it's my change in weight per day. Look at 0.39, 0.4 pounds a day. That's an extreme loss of weight, right? What happened? If you notice, look, most of these days where it spikes, we're watch. These are broken by week. These are broken by weeks. Most of the spikes occurred at the end of the week, like at weekend, right? Look here, weekend, Friday, Saturday. Friday, Saturday. This is a Tuesday. I don't know. Sometimes you just overhydrate, or But look at what followed after that, though. 3 days of. Yeah. Oh yeah. Oh yeah. Hey. No, I think this started. Look, this started. I think at 196 is where I started it. But when I actually first started, the day before this, I was at 200. That's when I was like, okay, that's it for me. 200. I got to drop weight. So in the first day or two, I dropped 4 pounds, and it was all water. So I didn't count that. Because it's not good. And when I used to compete in triathlons, I was my what I call my fighting weight, which was the weight I like to be at when I would do triathlons, was 158. That's 6'1" on a good day. Yeah, so that was like a rail, like just sickening looking. Yeah, people, my colleagues were like, "What's wrong? Is he sick? What's wrong with him?" But you have this thing called power to weight ratio. When you're going up hills and stuff on a bike, you have to carry your weight with you. So if you're all lean muscle, then you can move up the hill faster, right? So anyway, okay. That's obviously more information than you needed, but it's a good I hope that it's a good sort of connection to something like this, and how the function comes from the data, and then from that we analyze. So you have the homework assignment for that. I think that it's pretty straightforward. It's a lot of problems. They're asking for domain, intercepts, and vertical asymptotes. That's what I asked you to do on your own. Yes. Before Tuesday? Before Tuesday, study questions for the final. Right now, the only thing that you have are these 2 homework assignments. That's the only thing. I want to grade these tests. If these tests are good, then your final is not going to be cumulative. Like, it's not going to go back to everything. It'll just cover the new stuff. It'll be relatively short and sweet. But I need to grade these. So I'll keep that in mind, that you're requesting that. Yeah. Let me take a look at the third packet, because it's only 4:15. Let me just look at the next packet to see how deep we can go into this in a short amount of time. Whoa, what? Applications. How is it applications? I'm missing something. Where's test 2 packet? Is there something at the end of this I'm missing? You sure there's not like page 65 somewhere? And then this packet, am I at the top of it? Page 1? This is a pretty short packet. It's not too involved either. We can knock this out in 20 minutes. No, we couldn't. Yeah, you're right. What are we going to do next time? You're right. I do want to get into it. I would feel like I cheated you out of your money if you never saw an exponential function. But the thing is, with this, I think you might actually want something like this on the test because it's not difficult material. So it's something that you would. You're right. All right. So look, there's this section right here: application of exponential functions, and it's just a setup. Let me just at least set this up. That's it, and we won't get into any computations. How many of you have ever put money in a bank or taken out a credit card? Credit card's like a loan, right? I mean, and you have this thing called interest rates, and we have a formula for computing if you leave money in a bank, how much they're going to give you after amount of time, or if you borrow money from a bank, how much you owe them after amount of time. And it's called simple interest. And so we have a formula for it, all right? There's actually two formulas, and I'm going to write them down. The first formula is A equals P times 1 plus R over N raised to the N times T. The next formula is A equals P E to the RT. PERT, like the shampoo. Right, there's shampoo called PERT? E to the P, E to the RT. I don't think anyone's ever told me that before. That's funny. All right, so these are two different formulas. We use one of them in one case. We use the other one in the other case. I'm just going to talk about the first one today. We'll come back and talk about the next one next time. All of this formula, as bad as it looks, every letter has a meaning to it. A is the amount. I'm just going to write next to this because I can't squeeze it in on there. A is the amount of money in the account after T years. So the left side of the equation, what comes out of this is how much money you've got in the bank or how much you owe the bank. That's the N number over there. P is what's called the principal, and that's the amount that you initially put in or the amount that you initially borrow. So we're going to call this the original amount borrowed or deposited. So if I go to Best Buy right now and I get a credit card through Best Buy and I buy a big old entertainment system for $6,000, P is $6,000. All right? R? Nope. No, I mean, it would be negative to you because you owe it. But in terms of the bank is still going to look at it as that's money, right? So R would be here our rate, what we call the interest rate. And it always needs to be written as a decimal. In other words, if you go to Best Buy and you get their credit card, you borrow $6,000 from them, right? You get to go home with all that stuff, but you have to now owe them money, right? The interest rate on a credit card is most likely over 20%. So R in our problem would be written as 0.2 whatever. Like if it was 25%, it would be 0.25. You don't plug 25 in for R, you plug in 0.25 for R. All right, the next thing is T. T is time, and it's always measured in years for this formula. So what if you want to know how much you're going to owe Best Buy if you plan on paying it off in 6 months? You're going to use 0.5 for T. You have to know what, how to break down a year if you want to go shorter than a year. Understand? What if you want to pay it off in a month? Just 1/12, right? Whatever that is a decimal. Then convert it over to, yeah, just leave it as a decimal. All right, what's next? N. N is the one that always is confusing. I'm going to put it over here because I'm out of room. N is the number of times interest is what they call compounded per year. This is tricky. Well, no, this depends on the bank itself. Okay, so look. Let's say we borrowed $100. Okay, there's $100. Say we borrow it. Let's say the interest rate is 20%. All right, so our 20%. This is our P. Let's say we're going to leave it in there for 1 year. Right, so we're going to borrow it and pay it back in 1 year. And they tell us that the number of times it's compounded, they tell us, is 1. That means they're only going to compute your interest 1 time. So what is 20% of 100? 20? So you'd be paying back $120. Okay? But that's if they compound it once a year. A lot of times they could decide they're going to do it not once a year, but they're going to do it monthly. That would be 12 times a year. So, but here's the thing, it's tricky because that doesn't mean that they're going to do 20% of this once and then twice and then 3 times. What they're going to do, they will do it 12 times, but they're going to do it on a 1/12 of the money. No, not like that. What they do is they take 1/12 of the money, 1/12 of 100. Whatever that is, 100 over 12, and they compute the interest on that. And they do that 12 times. Yeah, so what winds up happening is that doing it once a month, or once a year, or 12 times a year, it makes a difference in how much money you owe, but it's not a lot of money difference. All right? It can be a few dollars, maybe. Yeah. Well, we're gonna plug it into the formula. We'll look at differences next time. Okay, N times per year. So look, what if they tell you that they're going to compound the interest annually? What's N going to be? 1 time a year. Semi-annually, what's N going to be? Semi-annually would mean how many times a year? Twice. So 2. Quarterly, 4 times. Yearly, same as annually. Monthly. Weekly, we'll say 52, although a lot of banks do 50 or something less because of all the holidays and stuff, but we'll say 52. All right? What if it was daily? Daily, 365, right? Well, most banks all do the interest the same way. They all do it what's called continuously. But that, again, we'll save for next time, because to do it continuously requires that we understand what this number E is, which y'all loved last time. All right? So you let me do one problem. That's it? One problem, okay? That's it. We borrow the $6,000 from Best Buy. We have a 23% rate, okay? They're going to compound let's say monthly. And they give you 18 months to pay it off. How much are you going to wind up paying at the end? So identify all the things. P is what? 6,000. R is, be careful, 0.23. Monthly means N is 12, and 18 months means T is 1.5. So A should be equal to 6,000, 1 plus 0.23 over N raised to the N times 1.5. So I'm using that first formula I gave you, right? Which is this one right here. And now get your calculator out. I recommend you do the inside parentheses first. These two right here are just multiplication. 12 times 1.5 is what, 18? So 6,000, 1 plus, this is 18. What's 0.23 divided by 12? And we're going to have to round this, but let's go a couple of decimals, not just one. Okay, 0.01916. Good enough. Let's go about 4 or 5 decimal places. Add that to 1 now. Order of operations, what comes next? Raise this thing to the 18th power. Take 1.01916 to the 18th power. On your calculator, you're going to have to know where that key is. If you don't know where the exponent key is, just ask me, I'll show it to you. Someone get that, though. Tell me what they get. 1.4072, something close to that? Everyone getting something close to that? I'm going to have to look at your calculator. All the calculators are a little different, though, so that's why. I'll show it to you if you can't find it. Now multiply that times 6,000. What is it going to be? So what is it? What does it turn out to be? 1,443. At that interest rate, your $6,000 entertainment package, you will have paid $8,443 for in 18 months. That's right. That's the way banks make money, right? Get a mortgage and see how much you pay. Because mortgages are even worse because all the interest is front-loaded. So you pay all the interest in the beginning. And, okay, I guess that's it.